I'll go ahead and start. Mr. Stephen Guy and I'm Ryan Graves. We are electrical engineering students at the University of Alabama here. And we created this system here with the help of our team as part of a senior design project. At the end of our studies here at the university, our last year or so, they tasked us with designing a complete system. And they'll judge that and give us a grade on that. And it's just to make sure that we are semi-competent, right? And that we can actually build an entire system and get it working. So at the beginning of last semester, our team was tasked with creating a solar-powered water purification system. The idea came about from the storms we had last April, and there was water available, but it wasn't safe to drink, and there was no power. So how are people going to get power, and how are people going to get clean water to drink? All right. Our project is department funded, and it is faculty supervised. Our supervisor is Dr. Timothy Haskew, department head of the Electrical and Computer Engineering Department here at the university. Our team members are Erica Boyle, Travis Cowart, Richard Fleischman, Stephen Guy, Krista Hart, and myself. So the goals and specifications, this is a set of goals that we came up with when we first came up with the concept for this project. We came up with a couple flow rates we wanted. We wanted about 2.5 gallons per hour of clean drinking water. And we also wanted about 4 gallons per hour of utility water. And we'll talk to you all about the differences in those two types of water here in a second. We also wanted to keep it under a 10-hour charge time. And we wanted to be able to run for at least 3.5 hours at these flow rates. We wanted to accomplish this all in one 24-hour period. Our total system runtime is 13.2 hours, if you will. And this is all assuming ideal weather conditions because we are relying on solar. So our system overview here, you can see we have our design mocked up right here. We have our solar panel, and that's going to provide us a DC voltage and ultimately power. We're going to run that through a DC-DC converter, which we're going to call the maximum power point tracking converter. We'll talk to you more about that later as well. That's going to go into a charge controller, which is going to charge up our battery, which is going to feed our loads, which in this case is mainly the pump that's going to pump water out of wherever you have it through the filtration system and ultimately out as clean drinking water and utility water. So system overview, this is a block diagram. A little more in detail here. You can see all of our subsystems in the blue tinted boxes. The yellow boxes represent different sensors, voltage sensors, current sensors, pressure sensors. All of these sensors let us know what's going on in the system. They let us know what's operating where and what we need to do to make sure our system continues to operate and what we can do to alert the user of what's happening in the system. So Stephen Guy's going to take me into a little more detail on these solar panel here.
Okay, this solar panel that we have has been donated by the faculty. We've been using it. Basically, it's a 40-watt panel. So at ideal conditions, we have 40 watts being drawn by this panel. These figures here are some tests that we've done. They're not to kind of let us know, basically as the sun hits it, there's different irradiances. Like today's a cloudy day, you wouldn't have a high irradiance. And the irradiance is, goes from 0 to 1,000. Perfect sunlight at about 76 degrees Fahrenheit would be 1,000 irradiance rating. So today would probably be around 800, meaning you wouldn't get as great of a rating. And that's the thing with the solar technology. Page down. The DC-DC converter is not necessarily is not necessary for our system. It's just kind of one of the requirements that our advisor has asked us to do. What it does is, in this technology with solar panel, it's not 100% effective, as in you're going to have losses between getting that energy and then being able to store it. What the MPPT converter does is it's maximum power point tracking. It converts the voltage to a level that will allow you to get the best efficiency that you possibly can. So basically it'll take in whatever the voltage is off that solar panel, converts it to something so we're able to store it in a more efficient manner. This is just a breadboard that we've converted on. This big round device in the middle is an inductor. There's some capacitors, different I guess elements that we use every day. Here is kind of one test that we've done with the DC-DC converter. Basically, It's a buck boost converter. It'll boost the voltage up if it needs to, and it'll buck the voltage down. And with this line that just popped up in the middle is at 6 volts. So half of the results should be below that line, and half of it should be above for the buck boost to work correctly. We've been using a solar simulator. It's a piece of technology. Instead of depending on the weather, we can set the irradiance with this device, and it lets us do lots of different tests at different times. Here's a power versus duty ratio, and right now with testing, we've only gotten 46% efficiency, which is pretty bad, and we know this, but with the breadboard that we're working on, it's going to lose a lot. So we're currently moving that over to a PCB. It's a piece of copper, and with these new traces, we should get much higher efficiency. Our charge controller, basically, this kind of takes in the voltage and allows us to send it out to the pump and to different loads, and also charge the battery at the same time. It's rated at 8 amps, and it has LEDs so that you know what's going on, if the battery's being charged correctly, and if you're getting the proper voltage you need. Here's a more in-depth diagram. You can see the 2 LEDs for operating status. It'll flash green if it's good, red if something's going wrong. And then different fuses, and you have your connection terminals down here. On the left you'll have where it connects to the solar panel, in the middle to your battery, and then on the bottom right to your loads. The battery, this is kind of the one piece of the technology that hasn't been advanced lately. The batteries are still kind of, a battery 20 years ago is still kind of the same thing now. But these batteries are specifically made for solar panels. It's a sun extender sealed lead acid battery. It's a 12-volt battery rated at 49 amp hours. Depending on your battery choice, you can have a higher amp hour rating, and it's just going to allow you to be able to charge longer and then operate longer. But this was the battery that we had been given by the department. These are some charging rates. Basically what we've done is we've taken different loads and applied it to the battery to see how long it discharges to 40% of the state of charge. You don't want to discharge it below that amount. And here's some discharging rates as well. We've also been testing output voltage over various loads. As you increase the load, the voltage of the battery will decrease and you will pull more current. So we had to test that in order to make sure that, I guess, with our microcontroller, to see if there's any control loops that we need to put in place, which Ryan will talk about later. The motor driving motor. With the motor, you can operate it anywhere from 9 to 13 volts, and we've tested it over these regions. Basically, the reason we're testing it is to see, can we drop the voltage down and operate for longer? You're going to get a slower flow rate, but will we be able to produce more water if we drop the voltage down? The motor drive will take in a voltage and then convert it to a lower voltage using a MOSFET and different other elements. This is the pump we selected. It's a FlowJet duplex DC diaphragm pump. It's supposed to rated at 12 volts. Like I said, we tested from 9 to 13 volts, and we tested it through the filtration system. With the motor drive, there's a couple elements you have to be wary of. With a microcontroller, which is kind of the brains of this whole project, you have to isolate that microcontroller so that if something does go wrong, which we hope it doesn't, but just in case it does, nothing goes wrong. There's also a few different elements that you can spec in order to make sure that you're protected. The main question with this project, though, is at what voltage should we operate? By using the motor drive, can we produce more clean water at one voltage versus utility water? It just depends on, I guess, what your preferences would be, as if you want, water to shower in, or clean drinking water. Here's a test we've done. Basically, as you vary the voltage, as the voltage decreases, the watt hours per gallon will decrease. So, like I said before, you can operate longer and with better efficiency as in power consumption. Here's a graph showing you want to operate at about where these graphs intersect. So right around 10 volts is where we're going to operate with our specs with our pump and filtration system. And here's utility water. Again, it's right around 10 volts. So with these two, it shows us we want to operate around there, and we should get the best results at 10 volts. And now I'm going to pass it to Ryan Graves.
All right, so we've talked about the electronics. So how does this thing actually work? The main goal was to clean water with this system. So this is a piping instrumentation diagram. You all can see these in industry. It describes the flow of water through our system and the various instruments associated with that flow. You can see here on the left we have a water inlet tank, which will be user provided. You have to go get your water, put it in the tank, and then it's going to suck, the pump is going to suck the water through that line through a strainer to clear out any of the big debris, because we don't want gravel flowing through the pump because it'll tear up the pump head and such. So it'll suck it through the strainer, it'll go through the pump into our first stage of our filtration system, which is a sediment filter. This is going to filter out your sand and that kind of stuff, the fine particles that get through the strainer but you don't want in your water. Next, it's going to flow through a carbon filter, which is kind of like a taste filter. It makes the water taste better, similar to the filters you put behind your refrigerator for your water output. Next, it's going to flow through another carbon filter. This carbon filter is designed to eliminate germs in the water, any kind of living bacteria or such. It'll get rid of that. And here's where the system gets a little weird with the flow. It flows out of that third stage into the clean utility water tank. Okay? This water is not perfectly clean of bacteria, microbes, and everything. What it's good for is basically if you're using soap with the process, say you're washing dishes or you're showering, something like that, this water is good for that. We got all the really bad stuff out of there with that, but it's still not perfectly clean for drinking. So you can either flow into that clean utility water tank, or you can flow into the fourth stage of the system, which is a reverse osmosis filtration system. What a reverse osmosis filter is, it's a filter with really small pores. Pores so small that only water molecules and smaller molecules can flow through it. Okay? So we're going to flow through that reverse osmosis system into another carbon block filter, which is going to improve the taste even more. Okay? And lastly, we're going to go through an ultraviolet filter. What this is it's a stainless steel tube. It's mirrored on the inside, and we put a UV lamp inside of that, something that you would see in like a tanning bed or something like that, except even more intense. And what this does is it kills any bacteria in the water, anything that's living, any microbes, it kills it. Anything with DNA, it actually destroys the DNA structure. So any viruses or things like that, it's all dead. It's all clean. It's perfectly safe to drink once you come out here into the water outlet tank, which we have a storage tank in the system, and we also have a faucet on the side of the system, which you'll see a little later, so you get perfectly clean outlet water. A little more on the filtration system. The filter system we used was just a simple one that you would find under your sink in a house if you're using well water or something like that. You see these a lot in rural areas. A little more, that picture on the left, that's your drinking water faucet. That's on the side of our wagon here. Picture on the top right, that's a flow restrictor on the clean utility water. We don't want all of our water flowing into that clean utility tank. We want some drinking water also. So we did put a flow restrictor on that utility water. And down here on the bottom right, that is our drinking water storage tank, which is in the middle of the wagon here. The inverter. This UV lamp that I talked about requires AC power. Solar is all DC, batteries are all DC. So we needed to invert the DC power into an AC power. What this inverter does is exactly that. You find this at a parts store, you can find this at Home Depot or Lowe's even. And what it does is it takes a 12 volt DC input and outputs 120 volt AC. The neat thing about this particular inverter is it also has a USB port, so it's a good thing for things such as charging your cell phone. We've got a second AC outlet, so you can plug in any home appliances that don't pull too much power and run those. We've also got the standard 12 volt car outlet that you see in your car to power any of those devices as well. The controller. Stephen talked about the brains of this system. This is a process. It's a miniature industrial system, if you want to think of it like that. So we need a controller. We need some way to control the actual process of what's going on. That's what this controller does. It's an Arduino controller. These things only cost around $60. They're not too expensive. We can read analog inputs, so we can read all of our water pressures at our different sensor areas. We can read our voltages and our currents, so we can monitor how much power we're getting off the solar panel. If we're getting any improvement from the MPPT converter, we can monitor that. We can also monitor how much power our pump is using. This is a picture of an oscilloscope with one of the signals coming off the microcontroller. That's a PWM signal. It drives the power electronics inside the system that we designed, the DC-DC converter and the motor drive. And lastly, implementation. This system was supposed to be portable. When we started designing this project, we pictured something you could put in your backpack and walk into a disaster zone with. Okay, obviously it got way too heavy for that. We've got probably 5 gallons of water sitting on this thing. We've got a battery, a solar panel. You're not going to be able to carry it. So we stole Stephen's little brother's little red wagon. and we transformed it. We rebuilt the rails of the system, and they support our pump, strainer, and motor. They support all of the filters you can see here on the front of the wagon, and it also supports our storage tank. We've got an aluminum enclosure on the back of this thing that houses all of our power electronics and our battery. It separates water and power completely. We don't want to start mixing those two. Our solar panel is mounted on top. It can pivot on its mount, so you can point it directly at the sun, because if you point the solar panel directly at the sun, you get more power out of it than if it was just laying on the ground somewhere. And here's a shot of the inside of our aluminum enclosure. You can see our battery sitting there. Our microcontroller is mounted up on the right back plane, along with our charge controllers and a couple of breakers. So water testing. Let's make sure this water is clean, right? What we did is last week we went down to the Black Warrior River, and we picked up a garbage can full of water in the back of the pickup and brought it back to the lab. Okay, you can see the before and the after shot. Our water testing. The input water from the Black Warrior River was gross. It was nasty. The pH was a little low. The alkalinity was high. The chlorine was all right. There was no chlorine in the water, but the hardness was also high, and the nitrates and nitrites were off the charts. These things, I mean, it was gross. If you can see this bottom picture right here, these are water test strips. You dip these in the water, wait a specified amount of time, and judge based on the color. According to this scale, you can see how much of whatever you're testing for is in the water. We're looking for white to pink on these bottom ones. We got brown. So, we ran our water through our system, through our clean utility water outlet, and we improved the pH to the 7.5 that you always want. We brought down the alkalinity of the water as well as the hardness, and our nitrates and nitrites were still present. Okay, we hadn't sent those through the UV filter yet. Okay, that was the problem. So our drinking water. As you can see at the bottom, they're white. Nitrates and nitrites are not present in this water anymore. Our hardness, our alkalinity, our pH are all at acceptable levels, as well as our iron and our copper. We also tested for lead. There is no lead in this water. There are no pesticides in this water any longer. And this bottom picture here of this purple vial, that's a bacteria test. So anything living in this water, which it's the river, there are microbes, there's all kinds of living things in this water. We put water in that vial, and this is a scale of purple to yellow. Purple means there's no living organisms in this water, and bright yellow means it's full of it. As you can see, our water is purple. That means there is no living organisms in our water. So how does this thing work? The operation. You must supply your own inlet tank, or you could just run a hose out into the creek, into the stream, something such as that. And you must provide your own clean utility water outlet tank, something you would collect the water in for washing dishes or stuff like that. The inlet water must be semi-clear and non-stagnant. That means don't go throw it in the ditch and try to suck the mud through the system, because it's not going to work. So if it's like a creek or if it's a stream, anything like that, we can clean that water. It'll be safe for drinking. Our operator panel on the system, you're going to have 2 switches. You're going to have a system on switch and a water on switch. System on is going to charge your batteries and run all of the electronics associated with it. And you could also power your home appliances or charge your cell phone off of that inverter like we talked about. And the water on means I want water. So it's going to turn the pump on. It's going to start monitoring pressures and such like that, and start running water through the system. The budget for this project, we ran it up to $820. The most expensive part of the system was the filtration system. The pump and the battery came in at a close second, third. So in conclusion, what we have done, we've built a portable solar-powered water filtration device, something that you could easily deploy into disaster areas such as after the tornado. We obtained our flow rates we wanted. We obtained 2.5 gallons per hour of drinking water and about 4 gallons per hour of clean utility water. We're doing all this using only 90 watt hours of energy. And we can actually run for 3.5 hours on one charge of the battery under ideal weather conditions. Are there any questions?